Well, hey there, and welcome to This Explainer. A huge shout out to the incredible team at Forge College for putting this together. Today, we're taking the theoretical why of access control and transforming it into the concrete how of Solidity mechanisms. I want you to think of today's session as examining an intricate architectural blueprint for a highly secure digital fortress. We're going to map out exactly how to build the secure walls, doors, and checkpoints in your smart contracts so you can enforce your rules with absolute precision. Let's get right into it.
Okay, let's dive into this structural blueprint. This naturally follows our previous lesson on Introduction to Deployment Scripting. Today we'll be covering the principle of least privilege, visibility as the first defense, guard clauses, modifiers, and finally, achieving defense in depth.
All right, kicking things off with Section 1, the principle of least privilege. Let's lay down some ground rules.
This concept is absolutely crucial. The foundational law here is that contracts must expose the minimum capabilities needed by each actor, period. I mean, if an address is assigned just to mint tokens, it absolutely should not have the ability to change fee parameters, right? It's kind of like giving someone a key to the janitor's closet and finding out, oh, wow, it also unlocks the bank vault. You want to give exactly enough permission to get the specific job done and literally not a single drop more. Understanding this design choice is necessary because it dictates how we apply everything else moving forward.
Which brings us to Section 2, visibility. This is your first line of defense.
And this brilliantly illustrates our compile-level defenses. Every visibility choice directly impacts the external attack surface of your contract. Take the external specifier, for example. It forms your explicit external API, giving you cheaper call data access, but it is fully accessible from the outside world. Then you have public, which creates the broadest surface possible since it allows both external and internal callers. Now on the tighter side, we have internal, limiting access strictly to the contract and its inheritors. And finally, private offers strong encapsulation solely for the declaring contract. You're basically deciding right here whether you're building a massive public gateway, a restricted internal hallway, or a completely hidden vault.
So exposing fewer entry points drastically limits direct attacks, but you really got to be aware of those public helper functions. Leaving a helper function public by mistake is literally like meticulously locking the heavy steel front door of your fortress, but leaving a tiny, unguarded side passage wide open. An attacker will absolutely use that passage to manipulate your internal logic. So always force the use of well-audited public wrappers instead of exposing your raw internal plumbing.
Okay, let's move on to Section 3, guard clauses. These are our runtime checkpoints.
So if visibility represents the walls and doors, guard clauses are the vigilant bouncers checking IDs inside the facility at runtime. You essentially have two types of bouncers. On one hand, we have require. Think of require as your standard polite but firm checkpoint guard. It validates inputs and callers, and if something's off, like say the caller isn't the owner, it performs a clean revert and returns a nice error reason. On the other hand, we have assert. Now assert is your dramatic no-nonsense bouncer. You only use assert for conditions that should never, ever be false, like impossible arithmetic. If an assert fails, it signals a massive internal integrity breach. Fun fact, in older Solidity versions, this dramatic bouncer would completely consume all your remaining gas just to make a point. So yeah, they definitely serve very different purposes.
Moving deeper, we have Section 4, modifiers, your reusable security gates. So what is a function modifier exactly? Well, it's a reusable language-level primitive that bundles pre- and post conditions to centralize declarative access enforcement across multiple functions. In plain English, modifiers let you name a specific security policy, like only owner, and apply it consistently everywhere. Instead of copy-pasting the same require check into 20 different functions, you just write the modifier once and slop it right on the function signature. This guarantees you never risk forgetting to lock a single door. But a quick tip, keep them short. They really shouldn't become long blocks hiding complex logic.
Let's move to and see how this builds, because these modifiers are incredibly powerful when you stack them. You can chain them together like a sequence of gates. Step 1 might be an authentication gate, Step 2 could be a time lock, Step 3 could be a quota check. But heads up, the order of these gates matters immensely. If you put a time lock before authentication, you might accidentally leak timing information to unauthorized users, or just waste precious gas checking a time lock for someone who isn't even allowed in. Always sequence your gates carefully.
Finally, we arrive at Section 5, achieving defense in depth, building the actual fortress.
This is where we see the mechanical synergy of everything we've talked about today. Step 1, narrow visibility. This minimizes your accidental exposure right at the compile level. Step 2. Guard preconditions, using explicit require and assert clauses to validate runtime conditions. Step 3. Apply modifiers, centralizing those reusable rules on your public entry points. You see, neither of these is completely sufficient on its own, but together, they create a robust defense in depth that makes your contracts incredibly secure.
Now, before we wrap up and prep for our next lesson on common access control use cases, I have a quick thought experiment for you. Which of your functions can be made internal or private right now? Seriously, take a mental inventory of the last smart contract you wrote. Are there public functions sitting there that really just need a named modifier? Are there checks floating around that should probably be centralized? Answering those questions is the very first step toward truly mastering access control. I want to say a massive thank you to Forge College for creating this explainer and making these foundational topics so accessible. Definitely go check out forge.college to continue exploring the amazing world of Web3. So until next time, I'll leave you with this. If a vulnerability scanner analyzed your contracts right this second, how many unguarded side doors would it find? Keep your logic secure and never stop building.